course, we can't change the pH of our cells very much. And there are small additions of acids, not particularly bases, but pretty much acids in our cells. And we'll talk about where those acids come from later on. But buffers are a solution. They are solutions that resist changes in the pH when there's a little bit of acid or base added. Not a ton, just a little bit. And so what they're made of is significant amounts of the weak acid and its conjugate base. If I had a solution, if I just made a solution of acetic acid, there would be already a little bit of our base in it. But remember, weak acids, out of 100 acetic acid molecules, only one would dissociate into the conjugate base, right? So that's not a buffer. You need to have significant amounts of both the base and the acid. So what we need to do is we need to scoop in more of that conjugate base. I can find in my lab a solid salt called sodium acetate that I can physically scoop in to a solution that already has acetic acid. And if I have close to equal amounts of these two, then I'm going to have a buffer. And examples are just going to be a weak acid. It cannot be a strong acid. It has to be a weak acid and its conjugate base. So let's take a look. This is acetic acid. And because ions don't exist on their own, right? I can't scoop out an anion. I can't go into my shelf and find an anion, right? It has to be the anion plus the cation, right? So that's where the sodium comes from. Okay? So I can go in my lab and find acetic acid. I can also go into my lab and find sodium acetate. That's what the conjugate base is. This is carbonic acid, and this is sodium bicarb. All right? The sodium is there just to balance out. So let's take a look at this. Carbonic acid, H2CO3. I know the sodium is not really there for anything. Sodium isn't affecting the pH at all. So really what we're looking at is HCO3. Which one's the acid? Besides the word acid in the name. H2CO3, because we're comparing H2CO3 to NaHCO3. So the one with more protons is going to be the acid. The one with fewer protons is going to be the base. Now, is this a conjugate acid-base pair? Is this a conjugate acid-base pair right here? It is. I mean, obviously I paired them together. But it's a conjugate acid-base pair if they differ only by one proton. And they do. H2CO3 and HCO3 differ by one proton. The Na, again, is for you to ignore because it's just the counter ion because I cannot scoop out an anion. So what we're looking at here is HCO3. All right, how about this one? NaH2PO4 and Na2HPO4. What are we looking at? We're going to cross out the sodiums. So we're looking at H2PO4 and HPO4. Are they conjugate acid-base pairs? Yeah, they only differ by one proton. Which one's the acid? H2PO4. And then the HPO4 would be the conjugate base. How do buffers work? Now, what I'm going to do on the exam is I'm going to give you a buffer. And I'm going to say, so I'm giving you a test question at this moment. And I'm not going to give you what the buffer is. But I'm going to give you a buffer, and I'm going to say, write the equation that occurs when added acid is added, or we add small amounts of base. What is the chemical reaction? So right here, this H3O is the added acid. All right? We're not going to add more of the acid of the base. This is outside acid. So outside acid is added. You can do H+, I don't care, or H3O is fine. So the buffer here, we're taking the carbonic acid buffer. This is carbonic acid, and this is the bicarb anion. And when you have an acid in the base, okay, when we add in added acid, is the acid going to react with it? No, it's the base part of the buffer is going to react with the added in acid. So here is what you should write in your note. This is the base part of the buffer, right here, base part of the buffer. And then this one is added in acid. The base part of the buffer, added in acid, produces acid part of the buffer plus water. So that's what you're going to memorize. You're going to say, okay, when I have a buffer, I have a base and an acid. And when I add in acid, H3O, the base part of the buffer is going to react with the added acid to create the acid part of the buffer and water. And so what we're doing by adding in a little bit of the acid is just changing the relative concentrations of the acid and conjugate base. We've eaten up some of the base part of the buffer and produce a little bit more of the acid part of the buffer. So here, if we add base, hydroxide, then the acid part of the buffer is going to react with it. So the acid part of the buffer, this guy, is going to react with added base to produce the base part of the buffer and water. It can get confusing if you don't have this straight. Let's write it in general form instead of the example. So I have a buffer that's HA and A minus. I have significant amounts of both. The acid part of the buffer will react with added in base to produce the base part of the buffer and water. The base part of the buffer will react with added in acid, to produce the acid part of the buffer, and water. All you have to do for your exam question is figure out which one is the acid, which one is the base, and plug it into here. Okay? You need to know how buffers work. Absolutely. When we make up the buffer, if we have equal amounts of the buffer, then the pH is going to be the pKa. But what if we have an application that we can't really, we need a buffer, but we can't find a buffer system that has a pH exactly at that. I knew when I was at Regeneron, I had to work at pH 8. So I had to adjust the relative amounts of my acid and base in order to fine-tune the pH of my buffer to be at that. So if the pH is at the pKa, then the concentration of our base to acid is 1:1. If we are below the pKa, then we have more of the acid stuff on the bottom, right? If we are above, we have more of the stuff on the top, more of the base. But look how much more. If I'm just one pH unit below or above, I have 10 times more base, 10 times more acid than I do of the other form. If I'm 2 pH units away, then I have 100 times more of one of the forms than the other. You think that's good practice? Just so you know, when you are in the lab or in the cell making up a buffer, you have only a certain concentration that you can make up the buffer. I can't make a 5 molar buffer up so that I'd have lots of the other form, even though I'm at 1,000 to 1, maybe I'd have enough of the, because it's going to affect the cells, the concentration of salt will be too much, all right, or the concentrations would be too high. When I made buffers up, it would be 0.1 molar would be usually the concentration that I'd work with, because that doesn't really affect cells or proteins too badly. It's a nice background maintaining the pH. And again, when you're working in the lab or you're working in the cell, the added acid or base is not, you're not pouring a jug of acetic acid or a jug of HCl on a protein or in your, hopefully in cells. That's why you would die if you drank HCl. Right? So we don't have to prepare for the worst. However, it does get a little unwieldy, right? If I made a 0.1 molar solution and I was 3 pH units below the pKa, I'd have like 0.0001 molar, something like that, of the base, and like almost 0.1 molar of the acid. So there's not a lot of base around to absorb any added acid, right? If I'm up here 3 pH units above, I'd have a lot of the base around, but not a lot of the acid. So there really wouldn't be a lot around to absorb any added base. So when you, the buffer range is about plus or minus 1 pH unit from the pKa. So if I know that I have to work at pH 8, then I would search for a buffer that had a pKa, a weak acid that had a pKa of between 7 and 9. Just telling you, in reality, it's 2 pH units. When you're working in the lab, people throw that out of the window, and it's 2 pH units. No one will criticize you if you're 2 pH units out there. At least I wouldn't. But once you get beyond that, people will say, you're crazy. Right? So that's buffer range. Now the total, oops, I already said all this. Now the buffer capacity is the concentration of the buffer as a whole. It's how much do we have? And I said that there's a limit before. You can't have 1 molar, 2 molar buffer concentrations because it's going to mess with what you have. But you also aren't going to have 0.001 molar buffers because there's not going to be enough of them around to capacity. All right, so what I want to say is when I was in lab in my early days, I had a lot of time in my hands. And I used to take buffers and then just drop in acid and have a pH meter in there. Drop, 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 and watch the pH meter not move, not move, not move. And then all of a sudden it would go pop. What would happen? What happened when the pH, when I would add the buffer, and then all of a sudden in one drop, it went from pH 6 or 7 to pH 2. I exhausted the buffer. If I was adding an acid, which one did I exhaust? The conjugate base, right? So that's how I spent my fun time in my younger years. All right, it's some information you need to know. The phosphate buffer is the principal buffer in the cells. The carbonic acid bicarb is not the only buffer in the blood, but why is it a good buffer for the blood? I'm not just being weird, right? Am I controlling the pH of my blood? Right? By breathing. So what happens is, oh, this is another thing. When you were doing your titrations, and you got that nice light pink, and you put it up on the bench for everybody to see, and then like 10, 15 minutes later went by, the pink was away and it was clear again. Why did that happen? It absorbed carbon dioxide from the air. And I think some of you may have done this in a biolab where you actually breathe into a solution and you change. You did that? Yeah. Kudos to whoever your teacher was. So that's a good one. Because you're going to see that carbon dioxide, and this is, the acidification of the oceans. This is why it's happening, because we have more carbon dioxide in our atmosphere. When carbon dioxide gets absorbed by the water, it becomes carbonic acid, all right, which is an acid. So we have to, in analytical, we have to use carbon dioxide-free water. We can boil it to get rid of it, and we actually will do that a couple times. You can change the pH of solution by breathing in it. And we have hyperventilation by, wait a second. Is this right? Hyperventilation, you're going to keep more carbon dioxide. You're breathing.
Oh, yeah.
Then I don't know if this makes sense, because holding your breath keeps more carbon dioxide in. right? And is that hypoventilation? Oh, it does. It decreases the blood pH, right? And in hyperventilation, you're getting rid of more carbon dioxide, and you're increasing the blood pH. Okay, so this is right. So can you die by holding your breath? Can you?
Well, no, your body's been making
Yeah.
breathing.
Then you'll start breathing again once you pass out.
Yeah, so you'll just pass out. Yeah. So the buffer solutions you find in lab are called zwitterions. They have both the acid and the base on one molecule. It's kind of neat. And they're less likely to cause complications. You're not adding two different things. Tris, you can notice you have the positive. This is the base, and then here's the acid. So you can see that you have different things. A zwitterion has both positive and negative, a net zero charge on the molecule. You notice in chemistry there's a lot of like German things in chemistry, like German names for a lot of the chemicals. All right, so when we're going to pick a buffer, we're going to figure out what is the pH we want to work at. Look for a buffer that has a pKa close to that. Make sure that it doesn't interfere. An assay is just a test with the reaction or detection of the assay. Ionic strength means concentration. Is it going to be too strong, like in terms of concentration? And then is it going to be soluble? And it's not going to go bad, not biological. So I know that I worked with Tris because I had to work at pH 8. When I was undergrad, we used pipes because I had to work at pH 7. So it was, there's a lot of different ones. Tris I used to run into a lot.